Okay, so threading and concurrency with Python, which I'll go ahead and state, as we stated last week, that it's kind of ironic that there's even any threading implementation stuff at all in Python. When in truth, it's not real threading, but that doesn't matter. You can still speed up your programs with it. So, what is threading? I'm sure Jacob is also fairly familiar with this, at least as far as what it is. But threading and concurrency, according to the internet, is the decomposability property of a program, algorithm, or problem basically into parts. So you break down one task into many tasks and then have threads or workers working on them all at the same time. So there's a lot more that goes into like threading on a very low level perspective, but since we're doing Python, we don't really have to care about all that. But threads are handled by your operating system, and threads are not processes, as a lot of people seem to think. So process is basically like the task that runs like your entire application, whereas a thread is something that runs within a process. So you always have one thread running that might be, that's like whenever you start up your program, if you don't have it multi-threaded, it still has one thread, the main thread of execution. So, and then threads, multiple threads can share the same address space while different processes don't, although threads can also not share the same address space. So, like I said, all that's kind of handled by the operating system. And if you take operating systems here, then you get to do a lot with threads. As I'm sure Hayden is, as I'm sure y'all are really enjoying right now. It only gets better. And I'll actually talk about some of the stuff in that. So, pros and cons of threading. There's really only one big pro, although it's a really good pro, and that's performance increase. So you can take a program that runs at a certain speed and reduce the speed or like increase the speed so that it takes like, I don't know, depending on the program and how well you write the code, you could speed it up by like 95% or something insane like that. But making it multi-threaded also is kind of harder to program, definitely harder to debug, because if you think about it, when you're debugging, you can view, like what line of code is running when, but if you have multiple threads running, then one thread is over here while another is in this function, so it kind of makes that difficult. And then deadlock is a big issue, probably the biggest issue with threading, which most of the slides here are about managing and keeping from happening. So deadlock is basically deadlock's basically when you have two or more threads waiting on each other. So if me and Isaac are sitting down having lunch together, but we only have one fork, only one of us can eat at the same, at once. Or, as I'll explain in a second, with the dining philosopher's problem, imagine if me and Isaac were having lunch and we only had 2 chopsticks, right? So there's the same amount of chopsticks as there is people eating, and if I pick up one chopstick and Isaac picks up the other, we can't really eat because we're both waiting on the other person to put the chopstick down. So that's essentially what deadlock is. You're like one thread is waiting on another thread while that thread is waiting on the other one. So you're constantly waiting. So the dining philosophers is basically exactly what I just said, except it's philosophers around a table eating rice with the same number of chopsticks as there are philosophers. So I mean, I guess they could like pick up the plate and rake the rice in, or as some person suggested in my operating systems class, break the chopstick in half. And yeah, Tang was like, no, you can't do that. So I guess you can classify that as operating system constraints. So, and for that problem though, there's a few solutions. One Dijkstra came up with, and I don't know the details, but it involved like numbering the chopsticks and having each philosopher or thread pick up like certain ones based off of certain criteria and all of that. But the simpler solution uses a mutex or mutual exclusion object, which basically just prevents a thread from executing what's called its critical section while another thread is in the middle of its own critical section. And by critical section, it just means if you have a thread running a function and it's like, say it's writing to an array or something, you wouldn't want another thread to start executing while that one's doing it, because it might be accessing that array and it might screw up. It might like change the memory in that array without the first thread finishing what it was doing. So you can drastically alter or completely make your end result like dysfunctional. So the answer to deadlock is synchronization. So as you'll see, there's a lot of ways to do that. Basically what you're trying to do is you manipulate the order of operation for the threads. Like you can make certain threads wait when you want, like, so instead of having two or more threads just run and enter their critical section whenever they get to it, you can say, okay, well, this one doesn't need to start doing this until thread A finishes. So you make that thread wait, and then thread A finishes, and that one starts doing whatever important task it is. And then sometimes you just want other tasks to run, like certain threads to run faster than others. You can do things to enforce that. Okay, so the first way of doing synchronization is using locks, which are like the most basic form of synchronization. And basically that's like, it's kind of like having a key. If so say there's the secret storage room in our EIT building here that has one key and one key only. Like if we're all threads and we need to access that room to get something out of it, only one of us will have the key at any given time. So say Jacob needs to go grab his cool decipher tool out of the secret storage room, and so he takes the key and goes into the closet there to get it, and then Cherokee is like, oh, well, I need my awesome web crawler laptop that's dedicated only to web crawling. And so she can't go in there and get it until Jacob comes out and gives her the key. So that's basically what a lock is. Yeah, he probably will. He's actually decoding all of the secret information in the closet. Yeah. Decoding the decoder itself with the decoder. Yeah. That sounds like deadlock itself. So yeah, when the lock has two states, obviously, locked and unlocked. When it's locked and another thread tries to acquire it, then that thread is blocked until the lock is unlocked. So that's a lot of times of saying lock, but it makes sense. Yeah, so then when a thread is done executing its critical section, you call release on the lock, and that is basically like Jacob coming out and hanging the key back up for somebody else to use. There's another special type of locks. I'm actually not sure if this is specific to Python or not, but they call it R-locks. And the only difference there is it will only block threads other than the thread it's on itself. So if you had thread A acquire the lock and then for some reason try to acquire it again before releasing it, then it wouldn't block that thread. So I'm not really sure what a good example of that situation would be, but it is a thing in Python. Conditions are another thing you can use to handle synchronization. So it kind of goes hand in hand with locks, and with conditions you can actually specify a lock. So basically you specify a certain Boolean predicate, so some kind of in Python it requires you to do something that's callable, so you could do a lambda or something simple if you didn't feel like you didn't have like a super complicated condition. But basically that'll return true or false, and then the condition will just use that, and if you pass a lock to it, whenever the Boolean predicate that you pass to it returns true, it'll unlock the lock that you passed to it. So I guess it's kind of a more automated way that you can use locks so that you don't have to just directly call release whenever you get done. Or I guess if you didn't know exactly when it was going to finish. So yeah, you can also have a condition instance notify all or any of the waiting threads or all of the waiting threads. And so yeah, the things I put in italics, by the way, are like methods on these instances in Python, but we'll get to that in a second. So yeah, you can call notify, and that just wakes all the threads that are waiting on that condition or that lock. It'll wake them up and they'll start running. And next is semaphores, which is, I really wish I had a marker, it'd be easier to demonstrate this, but a semaphore is probably the oldest synchronization object created by Dijkstra, and basically it has two things, or the two biggest things in it are an internal counter and a waiting list or a queue. So basically it's kind of like a lock, but it keeps a history of the waiting threads, and you can also adjust the counter when you create it to allow for like how many threads it should wait on, or how many threads it should allow before it starts to make them wait, and things like that. So again, it has acquire and release, and when you acquire access with the semaphore, it decrements the counter, and if the counter ever goes below 0, then the semaphore puts the thread that called acquire on the waiting list. You all see that in operating systems. Like, you have to do a bunch of tracing with semaphores. It's quite fun. But then when you call release, so when the thread is finished with its critical section and calls release, it'll increment the counter. So if you can imagine how that works, the semaphore is like kind of like a gatekeeper of sorts. So the counter is what tells it whether or not the threads that try to acquire will end up getting blocked or not. And then you can also have a bounded semaphore, which just also puts a maximum on there, so the counter value can't go past a certain amount. So I guess in the case that would be used in is if you have, like, if you set a bounded semaphore where the upper bound is like 5, and if you had 6 threads that tried to acquire it, then or not acquire. If you had six threads or something that try to increment it or something, it wouldn't go past that value. I'm honestly not sure on bounded semaphore as to how it's more useful or what, but regular semaphores are pretty useful, especially when you're dealing with synchronization with like memory access. Yeah, and the other two objects I have are really, really, really simple in Python. The first is events, and this isn't like typical events really when you're talking about events and listeners in programming languages. And this is like the event object in the threading package in Python, and it literally just has a flag that is either set or unset. So you can have basically whenever you go to start your action, you'll set the event so the flag is set, and then, or rather, you'll clear it, and then whenever other threads want to do something, then they'll check if the flag is set, and if not, they'll use the wait method, and it'll block until the flag is true. Yeah, and you could also use events even outside of multi-threading, because, I mean, since this is such a simple object in Python, like, you could use it, but then again, I don't really know why you would. I mean, with this, you could just use your own, like, conditionals, just a regular if, basically. So, I don't know, but it's pretty simple threading. And then the last one is even simpler, and that's a timer. So the timer object, you just specify a delay in seconds and then some callable function, and after whatever delay that you gave it, it'll run the callable that you passed. So yeah, real quick, I'm gonna go to the documentation. I'll show you. They have like a thing on that. So yeah, if you wanted to create one of those timers, like this is how simple it is. So you have a function. You can even do a lambda because it only wants a callable. So you just create it. You're gonna wait 30 seconds. After 30 seconds, it calls this function. So that's pretty simple. So yeah, and you can see this actually doesn't use any. But you don't think it uses threading. It uses threading underneath it, I think, because it's, this is in the threading package. But you could use this for other things too. Of course, Python also has like time.sleep, but I think the benefit of this is if you have code after you start the timer, I think it'll start that as well, so it doesn't wait like time.sleep would. Might try that actually. So yeah, we're pretty much to the examples. I just had one other thing, and that's with Python. I don't know, you may have seen the with statement before. A lot of times it's used like for opening files. So they'll do with open your file name as f or something, but the threading library did something pretty cool with it, so you don't have to actually call acquire and release on all of your stuff. You can just use a with statement, and whenever the code gets into the with statement, it automatically calls acquire, and then when it exits, it automatically calls release. So that's pretty useful. So yeah, I'm gonna try that with the threading thing real quick. So yeah, we'll import threading. And then okay, yeah, so after start, the timer printed, and then 5 seconds later it prints that. So yeah, that's the benefit. If you did like time like this, and you did you couldn't, like, you literally couldn't do it the same. You'd have to do time.sleep 5, and then you would just have to call hello. So this is all very linear, while what I had before is using threading. So that's pretty cool. This isn't the most useful for hardcore synchronization though. Like if you were trying to use that to make sure that something wasn't accessing any shared memory at like while another thread was, this wouldn't be a good thing, because the amount of time it takes for that to do that isn't fixed. Like, you know, it depends on the machine you're running it on, and all that. And then also you might specify too much time and you end up making it take longer than it needs to. So timer shouldn't be used for that kind of situation. But yeah, it's still there if you can think of an application to use it for. Alright, so I got some other examples up here. Not a whole lot, but so this is basically how you'll go about creating threads. I'll go through a couple ways actually with Python. So one way is to actually create a class. So I made a class called myThread, and it is a child of the thread class. And then you only have to override the constructor and the run function. So the constructor, you don't need all this stuff in it. Actually, you don't even need to override the constructor, I don't believe. So the run function is the only thing that really matters. That's what's going to actually get executed when the thread starts. So here I created the threads and I called start on them. So that's what's actually going to get executed then. So with this class, if I have an instance of it, when it runs, it's going to print that it's starting, and then it's going to do this. This function here is kind of like the critical section of any instance of this thread that I make. So we're pretending that this is a really complicated calculating mass thing. I don't know. You can use your imagination. So I kind of took part of this stuff from an example that I found. So it could be made simpler, but basically what that class allows me to do is when I create it, I'll specify a time here. So it'll alternate, it'll block the thread every 1 second. So for 1 second it'll run, another second it'll block, another second it'll run, alternate. And then this one is the same thing, but every 2 seconds. So yeah, so the actual function I'm calling here, you can see, yeah, it's just a for loop for the counter that gets passed in, which I passed in 5 for both of them, so they're both going to iterate 5 times. And each of those times, like I said, it'll make the thread wait for a certain amount of time. Yeah, so then I created them and started them. So if I run this, starting thread 1, 2, and since thread 1 had only a 1 second delay and thread 2 had a 2 second delay, you can see the thread 1 kind of does its things a lot faster than 2 does, and it ends up finishing first, and then thread 2 finishes after that. So that's a pretty simple way of doing it. For large scale applications, you're pretty much always going to be writing a class for it and overriding the run function. But there's another way you can do it, which I'll show you in this. All these examples are just modified versions of the previous one, really. So in this one I have the same class there, but I have another function called calculate density. It's also super complicated. It's just 2 for loops that have a whole bunch of iterations. So the first thread gets created the exact same way, but the other one, this is another way you can do it with Python's thread object. You can just specify a target, which is a function, the name of the thread, or whatever name you want to give it, and then arguments for the function that you passed in. So in this case, I had thread name as a parameter, so I needed to have an argument list. So that creates them the exact same way. So now the first example was running the exact same function with 2 threads, but the second example here, this thread is using the class, so it's going to be doing calculate mass, while the second thread is going to be operating on calculate density. So this is more realistic. You have 2 different threads, or 2 or more threads, doing different tasks at the same time. So now if I run that, see thread 1 is working, thread 2 is running at the same time because we see it started here, but since that's just a for loop and there's no output in there, it doesn't say anything on thread 2 for a little while, and finally thread 2 finished. So yeah, that's running 2 different tasks at the same time. So if you think of like a real application, you might have one thread like downloading images from a page or something, while another thread is like creating a directory structure on your local machine if they don't exist already or something. So it depends on your application, but that's more realistic, having different threads do different tasks. The third example, this is where I started getting into the synchronization. So it's the exact same, except this time I made a dictionary, or a map in other languages, called calculations. So the calculate mass function, which thread 1 is dealing with, it stores the mass here, but pretending for some reason we need the density to be able to calculate the mass in this function for whatever reason. So it's trying to access this record in this dictionary in order to calculate this. So that's fine, but the calculate density, the density record in that dictionary doesn't get stored until this runs in the calculate density function. So if you remember, when we just did the previous example, thread 2 finished after the first one. So basically it took longer to run this than it did this. So what's going to happen is this is going to try to access that record, and it's not going to be there yet. So we'll end up getting a synchronization error. Well, it won't say synchronization error, but that's what it'll be. Yeah. So thread 2 starts, thread 1 is working, finishes that one, and boom. So it has key error density because that key doesn't exist in the dictionary yet. But what's interesting is when you're using multiple threads in Python, if you have an error on one of them, the other one still finishes, like the other one still executes, or the other ones. So I don't know, that's kind of interesting. Of course, it doesn't matter. You're probably still, most likely you're still going to have issues because one of them had something go wrong. So in order to fix that, first I'm going to show a really cheap way of doing it, which probably actually you can do with the Python threading library, but it's not really anything to do with synchronization. So this is a cheap way. So on the calculate mass function, which finished first, all I did was, the threading library has a active count method in it in Python that tells you how many threads are running. So like I said, there's always the one main thread that's running, and in this case I created 2 more. So if there's 3 active threads, then we know that the calculate density one hasn't finished yet. So I just tell it to wait for half a second. So that's, like I said, not a very good way of doing it, but we'll show a better way in a second. So now thread 2, and they both finish. So you can see thread 2 finished, so the active count went down to 2, and it stops telling it to wait for half a second. Everything else I didn't change. The more appropriate way of doing that or one of the more appropriate ways would be to use a lock. So I created the lock beforehand. This is just a general lock that I can use. And then in the threading class, just for the sake of using the lock, instead of passing in the function when I created the second thread, I converted that one into a class too. So now I have my thread 1 and my thread 2 classes. So in the first one it does calculate mass, but in the second one it does calculate density. So really with the lock, you just surround your critical section with acquire and release with the lock. So that's just like I was saying with the that kind of analogy earlier. Has the key, goes in, does its thing, and then hangs the key back up. And then this one will do the same kind of thing. So when this one goes to get the key, if the key's not there, then it has to wait for the key to show up. So yeah, and then when I started them, you'll notice I swapped these two lines. So I started the second thread before the first one, and the reason I did that is if I didn't, we'd still have the issue with this one trying to access the density record when it's not there. Because what would happen is the first thread, this class here, this one would start first, and it would acquire the lock and then go and have that error, and the second one would be waiting. So we want this one to finish first, so that's why I ended up starting that one before thread 1. So if I run that, we'll get the same output. Should. Or no, we won't. Yeah. So thread 1 the way that it'll work with the lock is thread 1 won't even start until thread 2 completely finishes. So really that's actually a bad example of making this multi-threaded, because everything operates in a very linear fashion. So that's really not any different than writing this program to do, like, instead of all this mess, if I just wrote calculate density, calculate mass, and left it there like that, because this is going to finish and that one's going to finish. So yeah, that was a bad example actually, now that I think about it. But that shows you how locks work. Yeah. And of course you don't have to have a lock around this. You could have it within the function too. So that, because whatever thread is running that current is currently executing is the one that it's going to wait. It doesn't matter actually where you put acquire and release. But like I said, with this little Python tip with the with statement, so this is kind of, you may just be lazy like me, or you may just want to do something kind of cool with Python. So instead of doing thread lock, acquire, and release, you can just say with thread lock and do that. So it kind of handles all that for you. It'll run the exact same way. And then there's the R-lock. Oops. Oh, that's cool. I didn't know I could I'm not sure how it's actually working on that one. Apparently I can jump to the implementation of threading. Yeah, so there's R-lock, which isn't going to change anything at all in this case because I didn't do anything. If I did put something, I haven't really thought about this, so I don't know exactly what it's going to do to it. But so this thread would be running and it's acquired the lock, so any other thread can't acquire that lock. But since I'm using an R-lock now, if I call acquire again and it's the same thread as running it, then it won't block that thread. Honestly, I don't think that'll change it either, because it's running to begin with, so it's not going to affect it. Yeah, I guess that's a way to, I guess the purpose of R-lock is it's nothing about the same thread. It's just when you don't know which thread might be running a certain bit of code, if you're using an R-lock, then you don't have to worry about accidentally blocking the thread that you're currently on. Yeah, I don't know. That's kind of weird, but yeah, that doesn't do anything different. And that's all the examples I have. Actually, I didn't do any of the other objects, but here's the threading documentation. We can kind of go through that real quick if y'all want. So like I said, they have active count. It tells you how many threads are currently in existence, and then current thread is going to return your current running thread. These are all pretty straightforward. Gets the name of the current thread, or no, this is the ID number. You can get the name. So main thread, this will always exist. And set trace, this is like, I believe this is for, yeah, I believe that's just for debugging. And then set profile is for logging, I think. I haven't messed with those. And stack size, that's kind of cool. I've never done it, but you can actually specify the stack size when creating threads, I think. Yeah. And they suggest, like, yeah, using multiples of 4096. Yeah. So that's kind of cool. Me and Adam talked about this one time. I don't think Python lets you, but it would be nice if Python allowed you to specify the stack size for, like, just your program. Like with Java, apparently, like when you compile it in C++, you can too. You can modify the stack size. It's kind of nice, but I don't think Python has anything like that. I'm not sure, like, to what extent you can do it with threads. Timeout max. So yeah, timeout max you can just pass to the acquire functions and stuff. That just, if it's waited for so long, it'll time out and raise an error. Yeah, thread and local data is like, you can have variables that are specific only to the current thread that they're running on. So actually, I wish I kind of want to look at some point to see how they implemented this. But if you create this local instance like this, then you can just put dot anything really. It's like it keeps that variable name. I don't know how they like overrode, if they even did override the dot there, but I'm not sure how that works. But it is pretty neat. Yeah, and then thread objects. So also it talks about daemon threads. If your program is demonic, basically that means that if all it sounds funny talking about that so casually. If your program is demonic, your computer's probably possessed, and you should get a new one. It tells it somewhere in here, I think. But if your program is demonic, that means that when all the threads finish, I believe that it just closes. I don't know. Let's see. I know I read it in here more specifically. Yeah. So if you have I think I have it. I may have it backwards. Demonic is when it does run in the background, I think, yeah. And then you can have like semi-demonic programs too. So certain threads can run in the background, others don't. I don't know. But typically it's better to keep it non-demonic from what I understand. So I guess that depends on your application. If you're making like some kind of thing to notify you, like if you're making a reminder application, then it would most likely be demonic. So yeah, the thread object. I actually didn't use join, but join is something you use a lot. So you can, if you create a thread, you can call it join to wait until the thread terminates, and as it says, blocks the calling thread until join is called, or until join finishes. And you can have a thread call a join on other threads. So if thread A is running and thread B calls join on thread A, then it's going to wait until thread A finishes, until it starts executing the code after it calls that. So that, I guess, yeah, that's kind of a synchronization method too. And then the name of the thread with getters and setters. Yeah, it's a daemon. Right. So by default, yeah, daemon is set to false.
I think from what I'm looking up, it says the daemon thread basically if every non-daemon thread finishes, then every daemon thread just shuts off.
Right. Yeah. Yeah, I read that. I guess it wasn't in the docs.
Every article is something about Java.
If you use Java, you're a demon worshiper. Nah. And then yeah, it goes through all the objects I talked about too. So locks, it's got the methods and explains those, and lock acquire and release, R locks, acquire and release, conditions. So yeah, this is using the condition variable. Okay. Yeah. So yeah, with the conditions in here, you don't have to pass in a lock. I think if you don't, yeah, I was gonna say if you don't, it creates one for you. Yeah, otherwise a new R lock is created and uses the underlying lock. So that's all pretty straightforward. Semaphore is probably the most complicating thing in here, and it's not that bad when you get used to it. It's just you kind of have to plan whenever you're using a semaphore as to what value you're going to start it out with. So most of the time when I've used semaphores, most of the time you start the value out at 1, but it depends on the application. It is about to die. It's too bad there aren't any hacker rank threading things. Like I said, I don't think you could do that honestly on there with their server running it. I haven't. It's like we can do that. It's pretty much done. I was just gonna run through this. All this stuff talks about that. Yeah, I didn't talk about barrier objects, but yeah, I've never used barrier objects in here. I don't think that's a thing in other languages. I've only heard of it in Python's documentation here, so. Okay. So it's like you tell it how many threads can be going. Huh. Okay. See, and then they mentioned that with the with statement. That was pretty cool. The with statement is actually like it's there's a thing with Python called context managers, which I'm not an expert in explaining. Ben went on for quite a while once last year, and it was pretty cool. But if you're doing any Python and you want to make like some cool stuff with the with statement, though, you should look up context managers, like how to do things with them. I don't know. Since we got like a few minutes left, I don't know, I'll try doing something on HackerRank here, see what what it gives us. Could take a solution to like a previous one and then just add in threading. Huh? Yeah. See, like, I want to see if it doesn't spit out any errors for just using threading, then I want to see if it actually speeds it up. That would be pretty cool. Yeah. It's been like a month since more than a month since I've even been on here, and they've changed their site a little bit. Huh. Like they don't have the domains thing in there anymore. Okay. I'm sure it's still here though. Yep. First thought it was just gonna be a blank page. Oh, it's like the same thing, isn't it? Alright. There we go. I don't know, I'll just pick something simple. Sure. Hello world. No. No. How about that? Okay. Yeah, I should have just went to one of the others. Let's see. Got them all in here. Just find one. Pick quick. Alright. For threading. This may not have been the easiest thing to use for this, but yeah, because it's not something you can do super fast necessarily, converting something to, or making something multi-threaded. Also, I should note, like I noted before, threading only speeds a program up if you do it right, and programs can't always be sped up that much with it. If you do it wrongly or something, you can actually potentially slow it down. Listen, I made a generator between this, I think. Yeah. I did the yield, so I did a generator and then did it here, so that like kept it from spending so much memory. Alright. Alright, I can do it on this one. I think. Alright, so get lowest and add betweens. I'm going to try not worrying about synchronization first, and which is a bad idea, but we'll see. Code didn't pass. See? Synchronization issue. A variable was accessed before it was assigned. So that was in the get lowest thing. Or yeah, so this wasn't created yet. Did I do add betweens or get betweens? Yeah, I did add. Alright. So I guess what I'll do is make a lock up here. This isn't. I'm probably not gonna be. I'm not gonna be able to speed it up any. I don't think, without like really thinking hard on this one and like modifying it and stuff. Yeah. So. But I'll still, I guess, technically make it multi-threaded. So, with L. I should rename that. Not sure. Oh, okay. So this ran while that was running. I don't know if I actually needed the lock, because you can do you can do a function within a function. So I could do that and maybe try to do that. Thinking that'll work. No, because now there's another issue. Gen's not defined. Yeah. I don't know, this was probably a bad one to choose for trying to make multi-threaded on a very short notice. But you can do it on HackerRank, so yeah. I mean, I don't know if it's actually spawning different threads when you do it on the server, or however they have it set up. So I mean, but it appears to be. It runs, so at the very least, you're probably not going to hurt it unless you end up making things wait for long periods of time. But I don't know. That'd be cool to try. I guess I may try that on a simpler problem sometime. Anyway, it's 5 o'clock, so I guess that's